Good evening, all. Alan, sir, can we start, sir?
Good evening, ma'am.
Yeah, please.
Good evening, everyone. A warm and cheerful welcome to one and all present here. I am Hema Shriyar, your host for this wonderful evening, and I am truly delighted to welcome you all to the International Lecture Series Dialexi 2025 Physics, organized by the Department of Computing and Basic Sciences in association with IQAC and IIC at Christ College of Science and Management. We are deeply honored to have among us our beloved principal, Reverend Father Jins George CMI, our respected head of the department, Dr. S. Adi Lakshmi, esteemed faculty members, our distinguished guest speaker, and all my dear fellow students. Today's lecture will take us into the fascinating world of glass, light, and fast moves, a topic that beautifully connects science with innovation and technology. Before we begin the proceedings, let us take a moment to invoke divine blessings for the success of today's program. I request everyone to join me in a moment of silent prayer. Thank you. To begin this enlightened session, I would like to deliver the welcome address. Good evening to one and all present here. It gives me immense joy and pride to stand before you today as we get up to the International Lecture Series Dialexi 2025, organized by the Department of Computing and Basic Sciences in association with IQAC and IAC here at Christ College of Science and Management. On behalf of our department, I warmly welcome our beloved principal, Reverend Father Jins George CMI, respected HOD, Mrs. S. Ati Lakshmi, ma'am, Program Coordinator Dr. P. Rajalakshmi, ma'am, teachers, dear students, and our special guest, Dr. Nitish MM, who is a postdoctoral research in physics from Sapienza University of Rome, Italy. We are very happy and honored to have Dr. Nitish with us today. Sir, your knowledge and experience in glass, light, and fast movies will surely help us to understand how science connects with our daily lives. Once again, a warm welcome to everyone. Let us listen, learn, and be inspired by today's session. Thank you. Next, we are privileged to hear a few words from our respected head of department, Mrs. S. Adi Lakshmi, who has always been a guiding force and a source of constant motivation for the students and faculty alike. I now invite Mrs. S. Adi Lakshmi to address the gathering. Over to you, ma'am.
Thanks a lot for the intro. And respected resource person of the day, Dr. Nitish. Am I audible? Hello?
Yes, ma'am.
Yes, ma'am.
Yeah, my internet is showing it is not stable. That's why I'm just cross-checking. Okay. Okay. So, respected resource person, Dr. Nitish MM, we are really so glad to have you here. That is what I have to say, first of all, because it's been planned even a month ago, because our coordinators were back of us to have this kind of session, especially. And the choice of resource persons every time, I really wonder how exactly they are connecting the people across the globe. So it's truly an honor to have you today in this session through this international lecture series. And I hope this session, sure, it will be a fruitful evening to all the students who is connected today. So heartfelt appreciations to the coordinators for arranging such a lovely session. And I'm requesting all the students and the teachers who are connected, please be connected to throughout the complete session. And whenever possible, you please switch on your video so that the resource person also will have the liveliness. So it will be more interactive too. Okay, so thank you all. Thanks, all.
Thank you very much, ma'am, for your encouraging and thoughtful words. Now, I would like to invite Dr. P. Rajalakshmi to introduce our esteemed guest speaker for today's lecture. Over to you, ma'am.
Good evening, sir. So we are delighted to welcome Dr. Nitish M.M., a postdoctoral researcher in the Department of Physics at Sapienza University at Rome, Italy, as a distinguished speaker for Dialexi 2025 in the topic of glass, light, and fast movies. Dr. Nitish completed his PhD in condensed matter physics and from Pondicherry University, India, where his doctoral research focused on supercontinuum generation in barium zinc borate glasses. His research expertise expands in the material synthesis, characterization, and optics with a strong emphasis on a light matter interaction and ultrasound optic phenomenon. Before this doctoral work, Dr. Nitish contributed his instrumental automation in Z-scan experiments, showcasing his technical proficiency in the designing and executing laser-based optical studies. He's highly skilled in metal quenching techniques for glass synthesis, spectroscopical techniques, and laser-based experiment methods for material fabrication and fabric characterization. Currently, he's working in Sapienza University. His research focuses on Raman spectroscopy, nonlinear optics, and ultrasound laser matter interactions, contributing to cutting edge advancement in the photonics and fundamental material developments. Dr. Nitish has an impressive record of 15 international journals indexed in Scopus and Web of Science with a H index of 6 papers and I-10 index of 5 papers and totally over 150 citations over there. And his scholarly contributions reflect a strong commitment to advancements in the field of optical materials and nonlinear optics. With his passion for science and innovative research and global academic experience, Dr. Nitish continued to inspire young researchers and foster a deeper understanding of modern optics and material science. And it's over to you, sir. Kindly welcome.
Thank you so much, ma'am, for that wonderful introduction. Now, it's time for the most awaited part of the evening. Let's warmly welcome our distinguished guest, Dr. Nitish MM, as he delivers his talk on glass, light, and fast moves. Over to you, sir.
Thank you very much for the introduction and invitation. So, I would like to start the presentation right away. Yeah. Am I visible with the screen? Can you see the screen? Yeah. Okay. Okay. So, as far as I understood, the audience is a mixture of different specialized bachelor students. So, I tried my level best to keep it as simple as possible and to give a overview of the research I am associated with. So, I am, as they said in the introduction, I am Nitish M. working as a postdoctoral researcher in the Department of Physics at Sapienza University, Rome. Today, I would like to talk about uh, like a spectroscopic technique, which is ultravast spectroscopy, and its connection with glasses. So before beginning, I would like to mention that if you have any questions, you are feel free to ask in the middle of the talk. Also, it's not a problem. Also, you can ask in the end. It's up to you to decide. So I want to keep it. I want to keep it interactive because I think it's more better if you benefit something out of the interactions. So let me start with the presentation. So first of all, I would like to define what light is. So light, as you all know, light is an electromagnetic radiation which we can see with our eyes. Basic definition of light is like it's a part of electromagnetic radiation which we can see with our eyes. So this image here on the screen shows the entire electromagnetic spectrum. And the small part shown here is something which we call as light. So to appreciate the area which we are interested in it, I would like to mention that it is only a small portion of electromagnetic spectrum with a wavelength which is around 10 to the power of minus 6 meter. So first, I understand that many of you may not be familiar with the word wavelength. So I would just go to the basic. If you consider light as a wave, and the difference, the distance between two consecutive crests or troughs of that wave is called wavelength. And for the visible light, the light, it is around a micrometer, which is 10 to the power of minus 6 meter. And for a radio wave, it is around like 10 to the power of 3 meters, which is as high as a building. So this is a difference in the radiations involved in electromagnetic spectrum. So this is about light. Then why we are interested in it? Why should the light matter? This is the question we should ask before thinking about light. So this is something which is for you. If I ask any of you, you might be saying that without light you cannot see anything. True. So, but today I am going to speak more than what we see. It is something which we see beyond. Then you may have a question: am I going to speak about microscopy? Because microscopy is something you zoom into something and you see what you cannot see with your eyes. No, I am not going to speak about microscopy for today, but I would go something different, which is known as spectroscopy. Spectroscopy is a term which is used to represent or make. Spectroscopy is something which measures or appreciate. Like when you see a rainbow, what do you mean? You are appreciating different colors by your eyes. Instead, a spectroscopist will measure each colors and record it. This is what spectroscopy is about. So if you see a rainbow, you just appreciate it with your eyes. And in the case of a spectroscopist, he measure each colors and see how intense each colors are. This is what spectroscopy basically, in simple terms, it is what spectroscopy is. So today I am going to talk about spectroscopy, and moreover, I'm not going to talk about spectroscopy in a static term. I'm not going to talk about a system which is stable and I'm going to apply spectroscopy on it. No, I'm going to talk about an evolving system, a dynamic system, or a system which changes with time, and I want to do a spectroscopy of that. So then there comes the point of time. So you have to measure something in time at different moments. So this is something you can do with a camera. If you want to take a photo, I mean, if you want to capture, I mean, each time, you can take photos of each moment. Then you will have an information of each moment. This is what you can do with a camera. So it is similar to that. You are going to capture each moment in a way that you do a video, like you have a certain frame per second frame rate. So you capture each moment and you make it like a video so that you can understand what is happening. So to better understand this, I would like to show you how it happens. So this lady on the screen is a superhuman character in a recently released Malayalam movie. So she has some superhuman powers. I just chose her to be realistic with the situation. So in the screen you are seeing a part of the movie. They demonstrated like evolution of a kid to a superhuman character. So if you were supposed to take the pictures of the kid running, you have to have a camera which has a shutter speed faster than the speed of the person running. So if you decide to take it when she is a kid, it is very easy. You click, you get each footsteps. You click again, you get the next step. So you can go like that. But when she becomes a superhuman character, she runs very faster, and your camera is not able to take the picture of each moment. You miss some footsteps, so you see her at one moment, and you see her after 1 kilometer or 2 kilometer after certain amount of time. So your camera is not able to capture that essence of the moment, or you miss some information in the time. So basic idea from this slide I want to convey is, if you want to capture a dynamic situation or some evolving system, you need to have a camera with a shutter speed much faster than the movement. So you can also imagine like a butterfly flapping its wings. So you want to capture, you want to make a flying machine like a drone flying like a butterfly, and you want to understand how the butterfly flaps its wings to develop something similar. Then you have to have a camera which captures each of the moments of the butterfly wing flapping. So this is similar situation where you need a faster camera. So then you will ask why I need a camera beyond what we are having now. So the problem is in the time scales which we are going to study. So we are going to study a fraction of second, but a fraction of second much smaller than you can imagine. So how fast we need to be? So I will give you an example and will tell you how much fast we need to be. So to decide which camera we have to use, we have to understand what times we have to explore. What are the minimum time we need to have to see the dynamics of a system or a molecule or something else. So to understand that, I would give an example. So this is a schematic of a molecule in our eye. This is a very important molecule for our vision. This is a molecule there's a pigment in the eyes of humans. It is called rhodopsin, which consists of a protein called opsin and a chromatic molecule which is 11-cis retinal. So this is called 11-cis retinal because of these two hydrogen bonds, which are white colored balls here. These are connected to the two carbons, which are black, in the same direction, like they are on the same side of the carbon, like they are on the upside of the carbon. Because of it is called cis isomer. It's a cis isomer of retinal. The molecule is retinal and it is 11-cis because it is on the same side and it is on the 11th carbon. So this is the molecule inside eye which absorbs light, and this is something very important to generate a trigger for the vision. So how it works is when you are in this is inside the rod cells, which is essential for the vision in the dark. So when you see a light, So when you see a light, it absorbs the light and in 200 femtosecond. So I will explain what is a femtosecond, but the time is 200 femtosecond. This is a research done by some researchers like in 20 years before, and they found that this is happening. So this is an established result which says that in 200 femtosecond, it changes its structure and it becomes all transretinal. So you can see the change that here the hydrogen has flipped. So the molecule has rotated by 180 degree and hydrogen goes to the other side and the remaining molecules also goes to the other side. So it has the double bond between the two carbons rotated by 180 degree and the molecule changes. And this molecule, when connected to opsin, has a functionality to generate a signal. So it gives some signal, it triggers some signal. And this trigger causes a lot of reactions, following reaction to give us the vision. So this is, it has to communicate it to the nervous system, then it takes to the brain, then the brain interprets the vision we are having. So this is how it works. So the point I wanted to make here is that this reaction happens after the absorption of light in 200 femtosecond, which is very small. I will tell you how much is a femtosecond, but you have to understand that it is not a second. It is not something you can do with your camera. So even if this molecule and the system is very big, you go with your camera and try to capture it, you will not see anything in your camera because it happens in 200 femtosecond. And after this transition, it changes back to the original form. So you will see the same as when you take a picture, you will always see 11 cis retinal. You will never see all transretinal because it is short living. So this is the point where you need a camera which is faster. I hope you understand. Now, what is a femtosecond? So I think you are convinced the fact that we need to have a camera which works in a femtosecond, 200 femtosecond reaction. If you want to see a 200 femtosecond reaction, you have to have a camera like 20 femtosecond or 10 femtosecond shutter speed to see it evolving. This is the point. So then you will have a question, what is a femtosecond? So what does a femtosecond mean? A femtosecond mathematically is easy. Like 1 femtosecond is 10 to the power minus 15 seconds. So probably some of you will think, okay, it's 10 to the power minus 15 seconds. What is the big deal? You can even use a camera and see. No, it is impossible because the time is very small. To understand how small it is, I will give you an example. So this is, I just drawn a function of y equal to 1 on a scale of 0 to 1 seconds. So you can see on the x-axis time and on the y-axis a function of value 1. So if you cut this time, if you cut this graph into 2, you will get something like this, which lasts from 0 to 0.5 seconds. So, and you take the first piece, so you see this. Imagine you cut the first 0 to 1 second frame into 1000 pieces and take the first piece. So you have a interval of 0 to 1 second and you decide to cut it into 1000 pieces and you decide to take the first piece. So it will look like something like this. This is a frame which lasts from 0 to 10 to the power minus 3 second, which is 1 millisecond, like 0 to 0.001 second. Still we are very, very far from 1 femtosecond. So this, if you do this kind of activity iteratively 5 times, not on the first screen, but by like you have to take the 0 to 1 second frame, cut it into 1000 pieces and take the first frame. Then you take the first frame, cut it into 1000 pieces, take the first frame, then again you repeat it 5 times, then you will end up in seeing 1 femtosecond frame. So this is how small it is. So to appreciate it further, I can show you something else. So if you imagine a time scale of 0 to 32 million years, so you have to imagine that you are considering from 2025 to 32 million years back, then 1 second before is equivalent to 1 femtosecond. If you have a time scale of 32 million years, in that time scale, 1 second is equal to 1 femtosecond time. So this is how small it is. So you are going to explore, or you want to explore a evolving system in a femtosecond regime, you cannot use a normal camera or a normal something works on electronics. It is impossible, because with electronics you can go maximum up to nanoseconds, not more than that. So you need something which is faster. So this is the idea. So then the question is, you need to have, now we understood that you need to have a camera which is faster, and essentially you cannot have something with electronics, because electronics is slower. So you have to use the light which is faster, but then you have to know how to take the picture. So even if you have given a camera and you know the solution is in light which travels faster, so you need to have a fast traveling light pulse of femtoseconds, and how do we capture the dynamics? So this is the question. So this is a basic experimental setup for what is known as ultrafast pump probe spectroscopy. I will explain it to you why it is ultrafast pump probe spectroscopy. So we need to have two beams of light, and these beams need to be pulses, not a continuous beam of light which comes from the bulb. It needs to be some pulses of width in femtosecond, because it cannot last more than like if you want to measure 200 femtosecond, you need to have at least 100 femtosecond pulse width of the light. So this is the requirement. So your camera is going to be with the light, and you need to have two pulses of femtoseconds. And how do? You send the two pulses focused into the sample, and you measure one of them using a spectrometer. This setup here, the two boxes are together. It can be considered as a spectrometer. What it does is when it receives a beam of light, it splits the beam of light into different. It spatially separates the beam of light. Then it measures at each point, and it assigns some wavelength to each of the point, which is calibrated before measuring. So you get some points and you measure it as a wavelength. So this is just a camera, normal like a CCD. It depends on what camera you want, depends on the strength of the light, the intensity of the light you are going to measure. Normally in the spectroscope, you use a charged coupled device, which is basically a camera. You sensitize it with light, it gives a signal, a voltage, and it measures. So this is how it works. So what you measure is the probe pulse using a spectrometer. So the setup is like a general setup. This is not a particular experimental setup, but the general setup is like this. You have a pump and a probe. Why it is called pump? Because this pulse has to do something on the sample. So it has to initiate some event. Then the probe pulse will just pass through. The pump pulse do something, and probe pulse will just pass through and see what has happened. So our camera is exactly this probe pulse. The pump pulse has nothing to do with the camera, but pump pulse creates, like for the last experiment, pump pulse is the one which creates the change in structure, like it changes from 11 cis retinal to all trans retinal. So the pump pulse has to do that change. Then probe pulse has to explore and understand what changes has happened. And the rotating wheel inside here gives the possibility to explore what happened when the pump is on and when the pump is off, because you have two areas in this rotating wheel. One is open and one is closed. The closed region gives the option to understand what is happening when the pump is not there, and which you can take it as a background and subtract from the other result, which is the result of when the pump is on. Then this is you do it for a moment, then you move the probe in time back by some femtosecond, then you see what happens after this much femtoseconds after the pump has hit the sample. Then you move again probe and you understand what happens after 30 femtoseconds. Then you move again, then you understand at 40 femtoseconds. So in this way, you do it multiple times and you understand the evolution happening at a different time positions. So you collect this information and you can end up into a conclusion. So this is how it works. But there is a bottleneck. The bottleneck is that to do this, you need to have a femtosecond laser beam, femtosecond laser pulses, because the camera needs to act faster than the reaction or the evolution. So if evolution is 200 femtosecond, the camera should be lower than 200 femtosecond. So these pulses should be shorter in time. So in effect, the bottleneck of this experiment is that you need to have pulses short enough to see the changes. And as far as the technology has grown in the current age, we cannot have pulses of different colors. We can have only a fixed color pulses of femtosecond as of now. This is the limitation we are having. So we need to have a femtosecond pulse which makes some changes with a particular color. So this is a bottleneck. I will explain to you why it is a bottleneck. But now, for the time being, you need to have a pump which makes some change on the sample. And you can only have a femtosecond pulse, and the femtosecond pulse should have some color, a single color, not a gradient of colors. Okay. So now, moving on, to understand why it is essential to have a different color. I mean, what is the bottleneck of femtosecond ultrafast spectroscopy? We have to understand what light can do when it hits a material. So imagine you are seeing every day that light passing through the windows and light hitting everywhere, like light hitting a wooden block, light hitting somewhere. So what can light do? Light can do all these five things. And we are not at the moment. We are not very much interested in the last two things. But let's concentrate. Let's cover up everything. Then we will concentrate on the other three things. So I will start with the transmission. So you have to imagine light as a wave. Light is an electromagnetic wave, as I told earlier. So when it has a frequency, it has a wavelength, which means it is equal to an energy. So you can imagine in this way, like you imagine the material as a spring connected to a mass. So you have a material which is like a spring connected to a mass, which has a natural frequency of vibration, like it has a fixed frequency of vibration, like it is always the same. Then you decided to push it by your hand. This is equivalent to light, the incoming light. And if you want to push it by hand, if you are pushing, I mean, you have to do it like an oscillation. If you are doing it in the same frequency as the natural frequency of the material will respond. If you are very fast or very slow, very fast or very, very slow, the material will not react. It will just let it go through. This is how the transmission happens. So in the daily life, what you're seeing in the glass letting the light go through is because the incoming light, which has a frequency, wavelength, or energy, you can say any of them, it has a frequency which is much different from the glass. So it cannot do anything. It just passes through the glass. This is what it happens in transmission. And in absorption, this can happen only when the natural frequency of the material is equivalent to the incoming light. So if the light has a frequency which is equivalent to the natural frequency of the material, it will start oscillating with the same frequency. So it absorbs the incoming light and it starts oscillating in the natural frequency. This is called absorption. This you can see in the case of colored glasses, like there are some glasses which are colored where it transmits some light, but it absorbs some light. So this is a case of absorption. The emission is something like which happens when you are already oscillating. You are in a high energy state. The material is in a high energy state, and the intuitive, the spontaneous action of the material is to come down to lower energy state and stay stable, because the lower energy state is the stable state. So it has to, if it has energy, it has to get rid of that energy and come down to the lower state. This can happen by emitting some energy, and this process is known as emission. So these are the things which can happen when light interact with the radiation, with the light, when the material interacts with the light. So that two things are reflection and refraction, which happens when the incoming radiation, incoming light has a frequency which is not very far, but close to the natural frequency of the material. But for the time being, let's not worry about it's a radiation of the incoming light. For the time being, we can ignore them, but we are more interested in the absorption emission cases. So in the last slide, I said that for the material, to understand some evolution, the pump has to do something. So pump has to do something with the material, means the pump has to be in a region where its frequency is closer to it should be equivalent to the natural frequency of the material. So in that way, you are deciding that pump can have only a particular frequency or particular wavelength for the reaction to happen. So this is a bottleneck, because you cannot have a femtosecond laser of for different materials. You will have different absorption. So you cannot have a femtosecond laser for every frequency or every wavelength of the material absorption. So this is a bottleneck. Then, so you need to create a rainbow from the femtosecond lasers, because you only have one color of femtosecond laser, but your materials are different and they have different absorption. So you have to create a pump, also a probe, because probe has to be in a region where it shows something. So probe is also need to have colors which has some effect on the effect of the material to see something is happening. Because imagine you make you send the femtosecond light through a material which absorbs in red, and it has an effect in red and maybe somewhere near orange. Then you will not see these if you send a green beam. If you send a green beam, you will see nothing. You will see no changes. It's the same as before the pump, without the pump and with the pump. So you cannot conclude that it does nothing. No, because you are not looking at the right position. So if you look at the you have to look at the right position to see what is happening to the material. But the problem is that femtosecond lasers are not available everywhere. The typical femtosecond lasers, the high intensity femtosecond lasers, are available only for two different regions. One is at 1030 nanometer wavelength and one at 800 nanometer wavelength. So you need to create a rainbow from these two colors, like different colors of femtosecond beams. You cannot create a normal light because you need a camera which is shorter with the pulse width, like a femtosecond pulse width cameras. So you have to create a rainbow of femtosecond pulses from a femtosecond monochromatic single color beam. This is the challenge. And how you can get different colors? You all have studied, you might have studied in your high schools that when you send a white light onto a prism, you should get a rainbow, essentially. But this is not something we need. But to correlate, I want to tell you this because this is something similar. Like you create a different colors, a rainbow from a single monochromatic beam of light, and it is called dispersion. So this is something similar, but this is not what we want, because basically it is not a femtosecond beam. It is a normal light, like a light from sun or a light from a LED lamp or something like that, which is coming into different colors just because it was already with the different colors, because white light is composed of different colors. So the prism is just doing the separation, which is called dispersion. So there is nothing involved. It is just you're spatially separating each colors. So this is dispersion, which you maybe in your high schools teachers would have demonstrated to you in the lab. And the one we are looking for is something different. When you have a monochromatic beam, a single color beam, for example, here I am choosing a red color beam and I send it to a piece of material and it converts into a rainbow, like it makes a rainbow of colors. So this is different for two reasons. But the incoming beam is a femtosecond beam, and for the second reason, it is not the red is composed of all these colors. Red is always red. The other colors are generated by a complex process, which I don't want to explain in detail, but you have to understand that this is not the same as the dispersion, because dispersion has already had all the colors in it, while here you don't have the colors, you are generating the colors. So this process is known as supercontinuum generation. The supercontinuum means it is a continuous spectra of colors, like it has all the colors in it. So it is equivalent to the rainbow, but in a femtosecond scale, it is not the normal light. So now the question is, so if we need a we are convinced the fact that we need to have a supercontinuum generation to explore different materials. We cannot have a single femtosecond laser beam and study all the materials. It is impossible. So if you want to study all the materials, we need to have different colors, and which means we need to have a supercontinuum, and this can be tuned with tuning the pump, which is a laser, incoming laser, which we have only two sources, like one at 800 nanometer and one at 1030 nanometer. So if you buy a laser, which costs crores of rupees, and you have this fixed color, then you cannot say, okay, I need another laser to study another thing. No, because it again, also you don't have it in all the color regions. Also, if you have it, it can cost crores. You cannot buy every time a new laser to study something else. So you have to generate some different colors from the single laser. So this can be, the colors can be tuned by either changing the pump or changing the material. So I can show you how the material affect. The pump is more complicated. So here, if you look at the two plots shown in upper and lower panels, plot A and B, they used different materials. Like they used in the upper panel, they used YAG and sapphire. They look almost same, but still they are not same. I'll show you why it is not the same. But they look almost the same. But if you compare it with the lower panel, it is entirely different. So they have a different structure. So by chain, and they used another material, KGW by VO4, gadolinium VO4. So if you change the material, you change the spectra, you change the supercontinuum, the colors you see will be different. To appreciate the effect, I would show you something which is visually visible. So this is a supercontinuum. You can look at the inset. You don't need to worry about the graphs. You can look at the inset figures. You can see that two figures. One is generated with a calcium fluoride crystal, and the other one is generated with a barium fluoride crystal. So it is with the same pump. You pump, these dotted lines are pump. So if you pump with the same pump, you see a different spectra. Maybe it is not so convincing for you by looking at the spectra, but by eye you can see that they're different. They're entirely different. So you change just a material and you see this difference. So this is how a material can change the thing, change the supercontinuum generation. But then there are some limitations. There are there are some standard materials which can give a spectra in some standard regions, but the problem is generating in a region of spectrum which is not very common. Like if you want a spectra in the ultraviolet, it is not easy. And if you want a spectra infrared with a pump in 800 nanometer, it's not very easy. So there are issues like these which you need to solve to understand some dynamics of some systems which are very important. For example, in ultraviolet, if you want to study a biological sample, your pump needs to be ultraviolet, because all these tissues, proteins, cells, everything absorbs in ultraviolet. So you need to have some light in ultraviolet, femtosecond light in ultraviolet. So it's a challenging problem. So, but the existing materials, the crystals which developed by which is already in the market, can only give it in the most available region. So it cannot go down to ultraviolet or something else. So it's a bit tricky question. So this is the point where we see the future of glass. So before going to tell how these glasses can affect, let me explain what are glasses. So if I ask you what are glasses, probably you will tell that glasses are super cool liquids, which is something you have studied in your 8th standard or 9th standard by me. It is a common definition used in the textbooks, but this is not true. So I would like to enlighten with this fact that this definition of supercooled liquid as glass is not true. It is a subsection of glass. It is not. If you want to define glass, the entire material belonging to glass, you cannot define just like supercooled liquid. There are supercooled liquid glasses, but there are other glasses too. So the definition of glasses is glasses are non-equilibrium, non-crystalline state of matter that exhibit glass transition. But you don't need to worry about all this stuff. You have to understand the fact that glasses are not just supercooled liquids. They are non-equilibrium solids, which means that it is not at equilibrium. It is changing. It is evolving with time. So it is not a stable state. It can evolve with time. And it is non-crystalline. So the materials we see normally are ice is a crystal, but glass is not a crystal. It is a difference. So it is a disordered arrangement. So glasses does not have a periodic order inside its structure. But if you look at a crystal, you will have a periodic arrangement of structure. So glasses are non-crystalline state of matter, and they exhibit a particular thermodynamic property or phenomena called glass transition. Forget about it. It's more complicated, and I have shown it here, but it is something like it has to do with the temperature enthalpy diagram, and it exhibits a glass transition. So, but the important point here is that why we need glasses. So, what are the advantages of glasses? So, glasses are very cost effective. So, like you can make glasses. Bulk production of glass are very easy, very cost effective compared to the crystal production. So glass are cost effective and they have this combustion flexibility. What do I mean by combustion flexibility? Combustion flexibility means if you want to make glass of two powders, you decide that I took this chemical, and I want to make a glass out of it. You can make glass out of it. Ideally, you can make with any of the chemicals, you can make a glass. But the problem, the only problem is understanding at what condition they will form glass. In principle, you can make glass out of anything. So this combustion flexibility is something which crystals do not have, because crystals are a very ordered arrangement. They cannot form in any kind of structures. They can form in a particular structure. So it's not easy to make a crystal of any compositional form. So, but for glasses, ideally you can make it. And also, to some extent, by adding a glass formers or something like that, you can make it up with the composition you want. So in this way, you can tune the material with this composition. You can decide what kind of material you want by slightly tuning the material, which in crystal you don't have this flexibility, because sometimes there are some forms of crystals which cannot be formed. And moreover, it is simple synthesis. Like the normal glass synthesis is, as I was saying before, is supercooling. Like you bring down the temperature of the melt to room temperature very fast. So this synthesis method is very, very easy. And something I forgot to mention here is the recyclability. Glass are 100% recyclable. So if you create a glass, you break it, or you use it and you want to reuse it, you just need to melt it and supercool it at the same conditions. Like what were the conditions to make the original glass? Do the same for again, you'll get the same glass. So they are 100% recyclable. This is something promising for the future. So this is why I wrote the title of this slide as Glassy Future, because we are looking for some sustainable solutions in the world, and glasses offer it. There is nothing which can replace glasses. The only issue is if you think about getting something in the glass, the only issue is the fragility of the glasses. Like it can break easily. But these also we can solve it by tuning the composition, and people are doing it to make you already know that your mobile screen has a screen guard. Screen guard is made up of toughened glass, which is not something which breaks easily, but it is glass. It is not something crystal. It is glass. It is called toughened glass, and this is something an invention which is made by the people over the ages. So, I mean, it is possible that you can switch everything to glass and still be possible to use them. So this can be a future material for the. This can be a material for the future. Then, so I told you that glass are very important. So I want to enlighten you with how we make the glasses. So we make the glasses by normally in laboratory scale. We do a process known as melt quench. Melt quench is something like here I shown a figure. Particularly, I did during my PhD, but it can be generalized for any situation. Like you can take the constituent chemicals which you want to make into glass. You take it, and you using a mortar and pestle, you just ground it and transfer it to a crucible. Then you melt it in a furnace. So you have to go to a temperature. You have to know the temperature where it gets melted, because these mixtures behave differently than individual chemicals. So you have to find the temperature at which it melts. Then you go there and melt it and keep it for some time so that to have a uniform melt. Then you bring it down to a room temperature or a low temperature. Then it forms the glass. So you can see it here. It's really beautiful, like beads of glasses. You get exactly like this. So once you get these glasses, you have to. The problem with this is, like, you will have a lot of stress when you quench to room temperature. So you have to get rid of the stress. To do that, you have to anneal it. So you have to keep it in the furnace for not at very high temperature, but a very low temperature, which is below the glass transition. Then you have to decide what thickness you want. So you can ground it and you can polish it in a way you want. Then you get the glass. This is something we did. I did for my PhD. So you see a piece of glass which is as good as like you see in daily life. This is something very, very beautiful to do, to feel the pleasure of seeing exactly what you see in the daily life. You can do it by yourself. So then now, after preparing the glasses, we decided to study it for. I did it for my PhD also. Dr. Alan B. Samuel also did similar things. We prepared glasses, and we decided to study the supercontinuum generation from these glasses. So we put it in front of the femtosecond laser, and we record the generated spectrum using the spectrometer I have shown in the experimental setup, and we see some spectra. So, like, you can see that in the x-axis you have wavelength, and you see how intense they are at a different wavelength. The pump was like I used a pump at 800 nanometer, so the laser was 800 nanometer, a femtosecond laser of 800 nanometer, and you have some light here, 600, 700, and interestingly, the interesting part is that you have different glasses behaving differently. You can see that some glasses perform better than the others. This is in terms of the numbers, which I know, if I'm not a spectroscopist, I don't care, but I can show you how it's different for a layman. So you have to imagine like this. I put the glass in front of the laser, and what I see is this. So if I put the glass in front of the laser, I see this. But you have to understand that I'm sending just a kind of red color beam onto the glass, and I see all these colors. And for different glasses, you see difference. And you see the one glass which doesn't give anything other than a modified red. Other glasses also among them there are difference. So you can see a difference. And it's you don't need a spectrometer or like an instrument like this to see the difference, but you can see. So it's quite evident that by tuning the material, you can tune the color of light what you want, which is very much important in the sense that, as I was saying before, you need to have a pump and probe in a region where you have something happening. Like if your material is doing something in green light, you have to have some light in green. Not like if you go with the red, you will not see anything. So this is very much important. But the glasses we made is in the visible, performs in the visible, but it is important to have also some other regions of electromagnetic spectrum, tune it with the material, because this can give more information of the material. So this is not a direct implication of a direct advantage you can take out from the research to the society, or direct advantage you can take out to the technology. No, this is not something like that, but this is the basic of all research in the medicine, in biochemistry, biology, all other fields has an impact of this research, because based on this, you can understand what drug I have to prepare. For a medicinal biologist, you have to decide what drug can make a particular change. You have to understand what drug does. Also, if you are doing a cancer research, you have to understand what kind of, how does the cells behave when you are incident with a light? Imagine you want to study about the skin cancer. So when it is known that with the UV light you will have skin cancer, so you have to understand what happens when UV light incident on your body. So you need a source and a probe in the UV region. So this is something very much important for the development of the entire science, which is not very directly visible because of the complications in the research involved. It's very hard to convince somebody that you are doing a research on this to make the society better. So this is what I want to conclude about. And since I know that you have a background in different areas, I want to stress the fact that this is not just about physics, because when you are a spectroscopist, you have a lot of problems because with the you see some signal, but it is inside all the noise. So enhancing the signal to noise ratio is a problem. You have to get there are a lot of problems, like you need to have a proper mathematical knowledge to dig out the information from the signals. So it's not just being for the physicists. You can find application of this. You can contribute to this field through mathematics, through machine learning. We from our group, we had a recent paper on machine learning to get rid of the background of the spectrum. So there are a lot of applications. You can do it with computer science, you can do it with mathematics, you can do it with chemistry and physics. So it's a field everybody can contribute, and the results can be very promising in the field of the development of science and advancing of, especially in the fields of energy, medical science. There are a lot of efforts going on. So it's very important to have research in these areas of physics. Thank you very much for listening. I hope I could contribute something to enlighten you. Thank you.
Thank you very much, sir, for the truly fascinating and insightful sessions. Well, now let's have a short interaction session. If anyone has any questions, please feel free to raise your hand or share them now. Good evening, sir. I have a question.
Please.
Sir, will future filmmaking rely more on optics or AI-based visual synthesis?
I think this has something to do with. I understand. If I understood correctly your question, you are asking whether this filmmaking can be affected by the optics. Is that your question?
Yes, sir.
Okay, so this has more. The films we are talking about is more about molecular movies. Like you are going to explore what is happening inside a very microscopic samples. I don't know whether directors will be interested to see what is happening inside a human cell or like a chemical reaction, a photocatalysis or something like that. What is happening inside between two atoms? So if somebody want to make a movie on something like that, it will be very interesting. But for sure, this is something which can tell what is happening at a very low, very small time scales and very small, microscopically small particles, small regions. So it's quite interesting. I don't know whether they are interested.
Sir, how do these innovations in optics and sensors improve in realism?
This is a good question. I would say, like, I can say you an example. So, for example, in our society, there are a lot of people who is suffering from Alzheimer's. And this Alzheimer's is due to a particular misfolding of a protein molecule. So how does it happen? Nobody knows. Like, why is it happening and how fast it is happening? So there are some gray areas in the science where you don't know why it is happening, but it is happening. So you need to have a tool to understand why is it happening and how you can suppress it, how you can what do you say, like instead of giving a medicine, you can cure it before happening. So if you want to avoid this protein misfolding, what you can do to that cell. So if I know more about that protein, I will know how to suppress that protein folding. So this is something. I set an example in the case of medicine, but this is possible. Even imagine about energy, like the materials which are used for energy, like solar cell or batteries. So you develop the material in such a way that you know why this particular transport feature is shown by the material, or you can enhance it by doing something. So all this information comes from understanding what is happening at the microscopic level at very low time scales, so in femtoseconds. So what does the material do? So you are trying to understand the research. What we are doing here is very fundamental. Like it is very fundamental that we are looking at the electrons. So it's very fundamental. So, but the implications can take you like it can take you a huge success. It can take you to a huge success because the outputs will be change the entire understanding of the science. This is what I have to say.
Sir, how can the study of glass and light inspire creativity in art and science?
Sorry, again.
How can the study of glass and science inspire creativity in art and science?
Tricky. So I don't know really about how it can contribute to the art, but if it is about the glass can also the optics can contribute to understand the history. Like you have a lot of artifacts from the earliest periods of human. Like you have some artifacts. If you go to a museum, you see some artifacts which are very old, and if you want to understand how did they make it, and how we can what were they using, and what materials they used at that times, you can use optics to understand it. Also the glasses, there were a lot of artifacts recovered from the ground which are very, very old. So the glass making was there even maybe 1,000 years before. So the research in glasses can in that way help to understand our history better. Also optics, because there are optical tools which can understand like what are the materials in those artifacts and how old they are, and other information we can yield it from. So for the development of history, there is an impact, and for art, at the moment, I cannot. I don't know. I cannot say anything. Okay.
Thank you, sir.
So I see some question. Can light itself be used as a medium for creating or transmitting movies? Can light itself be used as a medium for creating or transmitting movies? Could you? I don't understand. What do you mean by? Okay, I understood. So you are asking whether the light can be used to send movies to somewhere. I mean, transmitting movies, I don't understand. Maybe if I understood rightly, do you want to speak? Do you want to explain your question?
Like projector, sir?
It's already there. So, I mean, maybe.
What is the temperature for the chemicals to burn to become a chemical?
Sorry, I didn't hear.
What is the temperature? Excuse me?
Yeah, sure.
Yeah, what is the temperature for the chemicals to burn to become a glass, sir?
Okay. So the glasses we made, I worked on, also Alan worked on, were borates, which require around 900 degrees. But if you work on silicates, it will be like 1200, 1150. So this depends. And there are organic glasses which you can make at 200 degrees. So it depends on what kind of glasses you want to make. And let me again understand what the question is. The other question which I missed: can light itself be used as a medium for creating or transmitting movies? As far as I understood, light is being used as a medium right now, for the movie, for transmitting the movies. And if you are speaking about in the beginning there was a question, if you are speaking about the femtosecond movies, I think I don't think that people will be interested to see what is happening inside a molecule. So if people are interested and directors are interested, it's quite interesting, because it's a lot of things and there are a lot of non-intuitive things happening inside the materials at the microscopic level. So it will be very interesting. Thank you.
So I'm having one small question. And as you've shown, usually glass is an insulator. Okay.
Yes.
And you have shown one picture that is, I think it is a photoluminescence picture. So
I can go
within
there.
that, the band gap, a previous
This
one. Yeah, this one, sir. Yes, sir.
Okay.
Within that is a box that is some band gap energy is given like 3.3 to some 5.8 electron volt.
Yes.
Is it belonging to a semiconductor?
It is not a semiconductor, it's still a glass, it's an insulator. This is the optical band gap, and what you are talking about is electronic band gap, which are slightly different. So these are the optical band gap we measured, and it's slightly different from electronic band gap, and they are still, all the glasses are they are not semiconductors, they are insulated.
Okay. And one more question, sir. So usually the glass which we are using in our mobile phones, so how it is connected to our with our mobiles? Usually, if it is an insulator, it won't transmit in conductivity.
This I don't know.
So,
This
I'm having a
but
wrong, but
I think
I'm having a doubt about it. So how this
yeah, but
glass is transmitting the heat and electricity? So I think you are a right
I
person
mean,
to ask.
I understood your question,
Yeah.
but I mean, I am not an expert of this, but I think it's not the what we say electric current which is getting transmitted,
Yeah,
but the
it's not.
stress we are putting. It's the stress. It's more mechanical. Like you touch it and you give a mechanical, like a piece of. It works like that, I think. I don't know. I never read about it, but I understood your question. But I may not be an expert to talk about
That
how
glass
it
is
works.
known as a gorilla glass. Something else in the.
No, the gorilla glass is the outer one. The
outer one. So even that it has some conductivity. When it is pasted in the top of the screen.
Yes.
When we are touching that glass, it transmits some
just
message.
Transmit the it transmits the stress. It transmits the amount of pressure you are putting.
Only through
I
pressure.
guess it is the thing. It is not, as far as I understood, the Gorilla Glass is a toughened glass. It has nothing very special properties. Like otherwise, it will not be cheap. Like you can buy a toughened glass for 200 rupees, a screen guard for 200 rupees. If it is not something which is, if it is something fancy, you have to pay a lot. I think it is not something like that.
Oh, okay. And one more doubt, sir. So all the lasers are super continuum?
No, the lasers. So there are lasers which are. So the lasers I spoke about are femtosecond lasers, which is a class of lasers which has a pulse width of femtosecond. And these lasers comes with a fixed color. Like normally the systems we have right now, the people which uses femtosecond lasers for this kind of experiment has two kind of lasers. One which gives a color 800 nanometer, and the other which gives a color 1030 nanometer. So these are the two lasers existing as far as there are other lasers, but for this purpose you cannot use because you need high intensity. So there are femtosecond lasers with low intensity, which you cannot use for this purpose because you have to generate some effect on the material. So you need to have high intensity. So there are other effects, other problems. So the for this kind of experiment, you need to have high intensity laser and femtosecond. And there are two in the market which are available. One is 800 nanometer and the other is 1030 nanometer. And they are very specific. They are monochromatic. They have a spectral width of 40 nanometers. So 800 plus 40, 800 minus 40. This is the maximum it can go. So it looks like a red color. And 1030 you won't even see because it is in infrared. So with eye you don't see anything. So these are the lasers we are having. But with putting some material in front of this laser, you get these colors. This is what supercontinuum is about. So even if you buy a laser of 800, you can get the colors in green and red and yellow wherever you want. Also, if you buy 1030, also you can get the colors you want. So this is the idea.
So in our lab, in physics lab, was in the students level, we are using one laser that is around 638 nanometers. It's a red color laser.
Which is a helium neon laser, probably.
Yes,
I guess, 632.
Yes. And
which is a red laser.
Yeah, red laser.
It is the difference between that laser and this laser is that red laser is a continuous wave. It is not pulsed. So here you have pulses, a femtosecond pulse. Like that laser is a continuous wave. Like if you imagine you have a light from a bulb. And you decide to send it in one direction. Light from the bulb is in all the direction, but you decided to send it in one direction as a line. If you are able to send it in a line, in a direction, if you are able to do that, this is something like you have in your lab helium laser, which is a directional and it has a phase dependence and it is in one direction. So, but that is continuous. Like you don't have pulses here. You have a light which is pulsing, like you see like a blinking, but with eye you cannot see because your eye is not sensitive to 10 femtosecond. But in principle you have a light on, light off, light on, light off, light on, light off with the femtosecond time scales.
Okay.
So this is the scenario. So the laser you see is continuous, like it goes from, it does not stop anywhere. It is, once you switch on, it is always on. But the laser we were talking about is it's pulses, like it is just a on off like that.
Okay, thank you, sir. And one more question. What is the specific application of this femtosecond lasers?
So there are different applications. They use it for like you can like modify the material, like laser welding. Like you can modify the material. You can, and there are femtosecond laser used to do surgery on the eyes, LASIK. I don't know. I don't remember the name of the surgery, but something like LASIK or something like that.
Okay.
They do a surgery on the eye with these femtosecond lasers. So these femtosecond lasers also, they used to modify the materials. Like if a material has a property like this and you want to modify it, you send a femtosecond laser on the material and you modify it because you modify the structure. So there are different applications. What I was talking about is more fundamental, like it is not an application kind of, you use it for application to generate something. No, it was something more to understand what is happening inside a material or what is happening at the microscopic level, to understand what is, what are the processes behind it.
Okay. Okay, thank you so much, sir.
Thank you very much. Okay, yeah. So this is a difficult question in the sense that for a common audience, I don't know how to explain, but let me try. So the question is how a laser can do pulses. So in normal light, you don't see pulses. So to do the pulses, there are two technologies used in lasers, which is called Q switching and mode locking. Depends on what pulse width you need. It's very complicated to explain. So I will give with an analogy, like how it will work. It is like you have a box. Imagine you have a box, and you decided to create something inside, and you want to keep a bulb inside a box. Then you decided to say that I don't want light all the time coming out from the bulb, so I close the box. But I want to have it after some time. So what I do is I let the bulb work all the time, but in the end I take it at a particular interval of time. I take the lid open and close, open and close at a particular interval of time, so that I have only that it is limited only as a pulses for different time scales. This is the simplest explanation I can give, but it is more complex. But this is how I can explain to an audience. This is not exact explanation, but I know. But this is the simplest way it can be explained. Like you keep a bulb inside a box, and you decided to take it on and off at some particular time of interval of time, like you show on and off with a shutter. It's similar to that, I would say.
Thank you, sir, for answering all the queries so patiently and making the session even more meaningful. Before we move to the vote of thanks, I would like to inform everyone that a feedback form link has been shared in the message box. I kindly request all participants to fill it out. Every successful event deserves a gracious conclusion. To express our heartfelt gratitude to everyone who made today's event possible, I now invite Ms. Kushma to deliver the vote of thanks. Over to you, Ms. Kushma.
A very good evening to one and all. On behalf of the Department of Computing and Basic Sciences, Christ College of Science and Management, I have the great privilege of proposing the vote of thanks for today's international lecture series, Dialexi 2025 Physics. First and foremost, I extend our heartfelt gratitude to our distinguished speaker, Dr. Nitish M.M., postdoctoral researcher in physics at Sapienza University of Rome, Italy, for delivering such an enlightening and inspiring lecture on glass light and fast movies. Your insights and depth of knowledge have truly broadened our understanding. Thank you, sir, for taking time out of your busy schedule to be with us today. Our sincere thanks goes to our beloved principal, Reverend Father Jens George CMI, for his constant encouragement, vision, and unwavering support in organizing academic programs that enrich both faculty and students. We also express our deep gratitude to our respected head of the department, Mrs. S. Dialexi, for her guidance, motivation, and continuous support in making this event a grand success. A heartfelt thanks to Dr. P. Rajalakshmi, Dr. Alan B. Samuel, organizing committee, and all the faculty members who worked tirelessly behind the scenes to ensure that this event runs smoothly. Finally, I would like to thank all the participants, students, and guests for your active involvement and enthusiastic participation, which made today's lecture truly engaging and memorable. Once again, thank you everyone for making Dialexi 2025 Physics a great success. Have a wonderful evening ahead.
Thank you, Ms. Kushma, for your kind and words. Once again, dear participants, please make sure to stay on.
Dear students, please fill the feedback form. So once you filled, you can get a certificate for attending certificate. Will be send it to your mail. Those who have filled the form, you can leave the session. Hello. Hello. Ma, good evening, ma. I'll talk to you 5 minutes later. I'm in the meeting, okay? Yeah, yes, sir. Students, try this form. If it is not open, I'll drop it in a group, students group.